Okay, so today we'd like to finish, almost certainly I won't. The section on application might have to be postponed until Friday, but I want to discuss the idea of radial quantization with what we've been building up to the last election. So having told you, just to recap the ideas of equal time, spoliation of space-time, and canonical quantization, and then talked a little bit about light-bulb quantization and how it frames things in a particularly neat way, solving the currents of motion, etc. That was really just building up to this idea of radial quantization, which is the more pertinent type of quantization from the point of view of conformal field theories. So today I want to cover the idea of foliation of space-time, not in equal time slices or large time slices, but in equal radii spheres. And then I'll show you how time evolution in canonical quantization equates to scaling in this radial quantization scheme, which will lead us to a very, very, very important statement known as the state operator correspondence, which tells us how to map states in Hilbert space to operators acting on points in space-time and vice versa. And then we will conclude the section with some observations about an important operation, that of propagation. In other words, not taking daggers or things, which is pretty straightforward in equal time quantization, but is a little bit tricky in the context of radial quantization. But it's just as important because being able to dagger things allows you to define inner products, and being able to take inner products allows you to compute correlation functions. And I've been saying over and over again as we've been working through the section that the observables that we care about as the conformal field theories are correlation functions. And so we need to know how to calculate these correlation functions. Okay. So the statement here is that radial quantization is the foliation of space-time and spherical shells of a constant radius. So in radial quantization, foliate space-time with constant radius, let's say R, spherical shells. Okay. And since it's the dilatation operator that allows us to zoom in and out in space, it will be the dilatation operator that will be responsible for moving between leaves in foliation in the same way that the Hamiltonian, this mission operator that we're all familiar with, was responsible for translating us in time. I'll show you explicitly how that works, at least in the Euclidean case. But the question that's worth asking at this point is, how is it that time translations in canonical quantization have become scalars in radial quantization? Let's see how this works. Let's work in two-dimensional Euclidean space. Just to make things concrete. So in 2D Euclidean space. In polar coordinates, the metric ds squared x squared plus dy squared just reads dr squared plus r squared theta squared. The space is topologically the plane, so it's topologically R2. So let's take this R2. And what we want to do is foliate it with circles of constant radius. 1, 2, 3, etc. Okay, so this is what I mean by foliation. So what I did in the previous case in d-dimensional spacetime was slide up my spacetime and spatial slices, right? And on each of those spatial slices, the time of the place will be equal to slices. Yeah, I'm showing how we do this with light slices and tangent to the light cone quantitation. Well, here we're foliating with these equal radius spheres or circles in two-dimensional plane. Each of these guys. In each of these guys, there's a little space of states. So each of these radius circles have a little space state defined. Okay. And time evolution in Euclidean time here is replaced by movement from smaller radius to larger radius circles. Okay, so time evolution goes from small circles to big circles. And I'll map this to something that's a little bit more familiar just now. But I first want to point out that again, the operator that's doing this mapping, that's taking us between the different leaves, is the dilatation operator. Okay, they tell us how to zoom out of the space. Okay, so evolution between leaves. By dilatation. So remember, I'm trying to convince you time translations between equal time slices in an equal time foliation becomes scaling in radial quantization, right? Yeah, this spherical shell foliating. So to do that, let me define a time here. And I'm using inverted commas here. It's not really a time variable because we're in Euclidean space, right? So now So I'm going to define this time variable t. To the relation that r, the radius there, is e to the t. So t is log of r. So what I'd like you to note here is that because this is the radius, r goes from 0 to infinity. So this guy goes from 0 to infinity. But t takes values between minus infinity and infinity to make that happen. Okay. So what does the metric look like in this new format? So ds squared, dr squared plus r squared d beta squared just becomes e to the 2t. T squared plus d beta squared. Okay. So we're interested in conformal field theories, which tells us that we can always rescale the metric by some suitable conformal factor. So let's choose then a conformal rescaling of metric by lambda squared. I'm going to choose e to the minus 2t. And if I choose this, and I implement a change in conformal chain of variables, then this will rescale the metric and ds squared is just dt squared plus beta squared. And then I ask, what is this? This is the metric of a cylinder. Okay, so this is just topologically cylinder. R process 1. So note that I'm not claiming that the cylinder is topologically, I'm not claiming that the cylinder is formally plane. It's not. What I am claiming is that the plane with the origin and the point at infinity removed. Okay, thinking about the plane as a complex plane, I identify all points at infinity at the same point at infinity, north pole. So if I remove the north pole and the south pole from the Riemann sphere, then that thing is formally the cylinder. Topologically makes sense, right? The twice part plane is just the cylinder. Right? So where that was the plane, what we've done is we've mapped this thing to a cylinder. Whereas r goes from 0 to infinity, t goes from minus infinity to plus infinity along the cylinder. Now, if I foliate this cylinder with equal time slices, it is a Euclidean Hamiltonian that trends me along these slices, t equals minus infinity to infinity. Okay. So the Euclidean Hamiltonian translates so in the cylinder, the Euclidean takes u between time slice t and time slice t plus something, let's say a. That's what accomplishes time translation of the cylinder. The question is, how does it look in radial coordinates? What is it in radial coordinates? Well, recall that R is e to the t. So as I translate along equal time slices of the cylinder, this goes to e to the t plus a, which you can get on top here, which is just e to the a times e to the t, which is just e to the a times r. So you can see how time translation along this cylinder that's conformal to the plane maps to nothing but a rescaling of r. Okay, so this is just a rescaling of the radial. So as I translate the time along the cylinder, I'm scaling up to bigger spheres in radial coordinates. This is the rescaling. So to summarize, in radial quantization, the generator that moves us along from one leaf to another in the spherical foliation is nothing but the dilatation operator. So and it plays a role in Hamiltonian in the sense that the associated time evolution operator along the leaves of the foliation is just u of t equal to I e to the I d t, where this t here is just the log of r. And again, u of t is a symmetry in a CFT, which means that the Hilbert spaces associated to each of those leaves in the radial foliation are the same Hilbert space. So if you think about what a dynamical system problem in this picture looks like. So a typical dynamical evolution would start by specifying some initial state at t equals minus infinity, at the slide at t equals minus infinity. This is the Cauchy surface, the initial Cauchy surface, in which I specify all the initial data, and then I evolve that surface forward with this time evolution operator. Right. And what this means is that I specify some wave function in the cylinder Hilbert space on the surface t equals minus infinity. And then dynamical evolution of this dynamic system is the same as time evolution along the leaves of this equal time foliations. On the other hand, as we've said, this Cauchy surface at t equals minus infinity, right, is mapped, the entire surface is mapped to the origin. So the same problem in the radial quantization, right, is specifying something at the origin. The entire Hilbert space on the t equals minus infinity Cauchy surface gets mapped to a single point on the radial and radial poles. Okay, and we're not used to thinking about states being specified at a specific point. But we are used to thinking about operators being defined at a particular point. And this is, in a sense, a very hand-wavy motivation for something called state operator response, which says that all the states that I specify here in this Hilbert space, one of the infinite number of equivalent Hilbert spaces, are mapped to operators in the radial constant. Right? The state operator corresponds to a very powerful tool in convection theory. And more formally, it states the following. It says that every state in a conformal field theory can be obtained by applying some local operator at the origin of the system to the vacuum state. So then here is every operator state. Every state and all field theory change. Yeah. Of some operator, some local operator at the origin. In equations, it says the following. Give me some operator, let's say phi, and I'm going to stay looking in two-dimensional system here. So phi is going to be some local operator depending on coordinate z is on the complex plane. If I take this guy and I act on the vacuum state 0, the limit that I am at the origin, so then Z bar goes to 0. This defines for me some state of phi in the Hilbert space. So phi is the state in the Hilbert space. And this guy is some SL2Z vacuum, or define what is at this point of this one state, state operator corresponds. So this tells you how to associate state to an operator, but vice versa, I can also associate an operator to a given state. Similarly, conversely, every local operator can be associated to some state, essentially by taking the limit of its action on the vacuum and the coordinates approach theory. So, given a state, say psi, define some operator psi. Given some state psi in the Hilbert space in CFT. Fine. An operator psi is there. By following. So I project the state psi to the SL2Z vacuum, and this defines for me the matrix expectation of the matrix elements of the operator psi. Since the conformal symmetry acts on both the state and the operator in the same way through state operator correspondence, it preserves state operator correspondence, preserves conformal symmetry. Okay, it doesn't really matter whether I'm talking about states or whether I'm talking about operators. I can execute this map between the two and make sure that whatever I'm talking about is still a conformal field. Okay. So it turns out we do. Yeah.
So given a state file, is it a trivial task to find the operator first field, or is it like only one?
Is it what?
Is it a trivial or easy task to find the operator file associated to the state file?
No, it's not a trivial task. In principle, it exists. Okay. So one important technical detail that we need to talk about before moving on to the idea of, well, the next section that I want to talk about is essentially conservation laws and Lewis theorem, but in this language. And before we do that, we need to discuss how to conjugate states and operators in radial conjugation. So, as I said earlier, the notion of conjugation is something that's quite important in quantum theory. This is because I need to talk about inner products, and I need to use those inner products to construct the probability. Okay, so there's actual practical consequences to having a proper definition of what conjugation is, what it does, how you use it to construct observable quantities. Okay, so conjugation is quantum QFT general. And particular. I mean, it's important in general, but specifically, if you want to talk about practical things, then you need it in order to construct observable quantities. So before going on to what's going, how to think about this in radial quantification, let's just recall what you should know already from a first course in quantum mechanics, or for that matter, linear algebra. So let's see how this would normally work in Minkowski space before going on to talk about radial quantification. In Minkowski space, since we need to use the Hamiltonian to talk about energies, which are actually measurable things in the quantum theory, we need to work with emission Hamiltonians. There's a caveat to this, because you don't necessarily need to work with emission Hamiltonians, work with a non-emission Hamiltonian, but it still needs to serve some subset of symmetries in the problem. These are what's called PTs of metrics. But I need real eigenvalues, and since the Hamiltonian is emission, is H. What this means is that the time evolution operator U of t that I can start from the Hamiltonian calculation satisfies that if I take its dagger, its emission quantification, and this is e to the minus I h t dagger, which is e to the I h t, which is e to the minus I h minus t, which is u of minus t. So the time evolution operator satisfies the property that u of t dagger is u of minus t. And this tells the effect that emission conjugation of time evolution to some time t is the same as time evolution to some time minus t. Right? And an immediate consequence of this fact is that if I take u of t dagger and multiply it by u of t, and this is u of minus t, u of t, which is u of 0, with the identity. And this is the statement that the time evolution operator is unitary. Okay. And this in turn ensures that the Hilbert space at early times and the Hilbert space at late times stay in Hilbert space. In other words, that that they're equivalent. In other words, that probability is concerned. And we take this to be a fundamental concept. Okay. So this is the statement that time evolution serves ability That is to say, is what we call. And we believe that all closed systems in physics are unitary. But we also believe that there aren't really any closed systems. Okay. So the question is, what happens in Euclidean space? So to go from Minkowski space to Euclidean space, I have to analytically continue time there. So unitary, sorry. So time evolution operator. Again, time in the Thomas here. Time evolution operator. Is given by u tau, say, and u of tau is e to the minus the Hamiltonian times tau. Okay, this is Euclidean time. We'd like to understand whether the conjugation works in the same way, namely in this way in Euclidean space. So again, in Gaussian space, I take the conjugate of the Hamiltonian conjugate of this u of t, and I have u of minus t, and this is what is called unitary. Okay. And then I constructed the associated operator in Euclidean space, and I want to know, does conjugation work in the same way? I need to actually set some bounds. So something that I'm willing to accept, something that I'm not willing to accept. So what am I going to give up? And what am I not doing? I would like to not give up unitary. I would like to still believe that a Euclidean system, those Euclidean system is still unitary. Okay, so if we don't want to give up unitarity, then we require that the following is true. So unitarity requires that u of tau, u of minus tau, rather, unitarity requires that u of tau, u dagger of tau, in identity, which would require us to force u dagger of tau to be u of minus tau. We still want real energies. So real energies are eigenvalues of the Hamiltonian. The real energies require that h dagger equal to h and both of these together would mean that I need to conjugate time. So in the Minkowski picture, I left time alone for the conjugation. Here it would require that tau dagger be minus tau. This is not surprising since you go from Minkowski space to Euclidean space. I make a weak rotation and analytic continuation. Not surprising. since with rotation continuing takes up between cosmic space and Euclidean space. To so let's see what we just learned. What we just learned here is following. So if you denote Euclidean communication by a double dagger, distinguish it from Minkowski communication, single dagger. I use this because of the big dagger. Come on. Okay. Double dagger. Then what we've learned here is that given some operator A of tau, then the Euclidean conjugate of A of tau is the Minkowski conjugate of A of tau, A dagger, but evaluated as minus tau. So in other words, in addition to doing the normal Minkowski conjugation and Hamilton conjugation, you also have to change tau to minus tau in order to enforce unitarity in the system. Okay. Okay, let me stop here because I've run out of board space. And we will pick it up on Friday and finish up by showing you that this is a little bit deeper than what it looks like. It's not just flipping tau to minus tau, right? Because we define Euclidean time for t earlier, for tau now, as the logarithm of r, r of e to tau. Flipping tau to minus tau is actually an inversion, and an inversion is a conformal transformation. Right. So in other words, when we conjugate operators here, it actually comes with an inversion as well. It has important consequences. Okay. All right. So let me stop here.
For the delta multiplication for the